and have actually, I read an article that there's some geoengineering applications of mushrooms, potentially. So, and from that, Morgan came here and really had a strong interest in, connecting science to policy, and really found public health as really the best pathway for that. And her capstone involved a lot of data analysis, but also a lot of integration to policy. So really strong job this year, and really my pleasure to introduce Maren Hale, our next speaker. The floor is yours, Maren.
But thank you, Corey. And hi, everyone. My name is Maren Hale, and today I'll be presenting my research on green space as an extreme heat adaptation strategy. So extreme heat is a major public health issue. It's actually the leading cause of weather-related mortality in the United States, and it has a wide array of health impacts, ranging from the direct, including dehydration and heat stroke, to indirect impacts affecting the cardiovascular, renal, respiratory, and other bodily systems. Certain populations are more vulnerable to the health effects of heat, including the elderly, young children, people experiencing homelessness, people who work outdoors, and also people who simply can't afford things like air conditioning. On top of this, climate change is expected to just make things worse, as climate models project an increased frequency, intensity, and duration of heat waves throughout the 21st century, and Southern California in particular will be hard hit by these impacts. So in addition to variation in who might be impacted more strongly, there is also a geographical variation in extreme heat. In San Diego County, on a given day, coastal areas are usually more buffered from heat than inland regions due to being next to the ocean. They'll usually be cooler. But during a heat wave, most of the impact is actually felt on the coast. And that's just because people who live further inland are more acclimated to dealing with heat. And they're also more likely to have access to something like air conditioning. Another key factor affecting the spatial distribution of heat is something known as the microurban heat island effect. And this is a phenomenon in which there's often extreme variability within a given city in terms of temperature, sometimes upwards of 7 degrees Celsius between different neighborhoods in the same city. The way this works is that buildings and paved surfaces trap heat, which you can see in this schematic on the left. And on the contrary, trees and other vegetation can actually have a cooling effect by providing shade and by evaporating moisture out of the soil. Living in a microurban heat island significantly increases your chances of facing negative health impacts or even dying from extreme heat. And on top of this, people who live in microurban heat islands are usually already at a disadvantage because the people who live in the densest part of the city are more likely to be people of lower socioeconomic status and people of color. The good news is that if trees and vegetation make such a difference, then we can actually do something about this. Planting trees and expanding green space are policies that can actually be undertaken relatively easily. The question is just where and how, and that's what my capstone attempts to explore. So the general idea of my capstone is to see how increasing green space in various parts of the county might help decrease some of the negative health impacts associated with heat. And I broke it down into 3 steps. Aim 1 was to understand the current distribution of green space in San Diego County. So which parts of the county have more vegetation, which are more built up or paved over, and what kind of measures capture this distribution. Aim 2 was to understand the heat-related health burden in San Diego and its relationship to green space. So which parts of the county face the highest hospitalizations during a heat wave? Are these the same parts of the county that have less green space? How strong is this correlation? And finally, Aim 3 was to create future scenarios for increasing green space and then assess their impacts on health. So what would happen if we increased green space by X amount in a given zip code? How many hospitalizations could be avoided? Where should we prioritize these increases in green space? So Aim 1, which again was just to understand the current distribution of green space. To do this, I had to map a variety of green space proxy data for the county, and I did so using QGIS on the zip code level. And I just want to explain the use of proxies. So green space is not something that you can just directly measure. There's no units of green space. You have to use other factors and measures that in some way indirectly represent green space. So I actually used 6 different measurements, but to simplify things, today I will only be discussing 2 of them, which are tree canopy and impervious surface cover. So here are 2 maps of 2 different green space proxies in San Diego County. The map on the left is tree canopy cover, and the map on the right is impervious surface cover, or the percent of an area that's covered by an impermeable surface, such as pavement or asphalt or things like that. So note that these 2 maps aren't exactly the same. Conceptually, they're similar in that areas with more open space and areas with less pavement should have more room for trees and vegetation, but obviously their distributions don't overlap perfectly. And that's why it's so important that I used a variety of green space proxies in the study, and also that I used this composite index, which aggregated all 6 of the proxies together. But regardless, you can see some general observations from these 2 maps, which are that there are generally lower levels of green space in the more urbanized zip codes, and roughly an increasing trend in green space moving inland and also moving northward. So the next part of the project was to understand the heat-related health burden and its relationship to green space. Again, I used QGIS to map heat attributable hospitalizations, and then I performed what are called meta-regressions between this hospitalization data and the various green space proxies. And this is essentially a way to quantify how changes to an effect modifier such as tree cover might influence an outcome such as hospitalization. And I'll explain that in a little more detail in a minute. But first, I needed to understand where heat was having the strongest impacts in terms of people's health and where it was having less of an effect. So this map represents the spatial variability in terms of where people feel the strongest health impacts of heat. And this data, which was compiled by PhD student Kristen Hansen, compared the hospitalization data between heat wave and non-heat wave days. And it depicts the number of hospitalizations that are directly caused by heat in each zip code for every 100 heat wave days. So here we defined heat wave days to be any day where the maximum temperature is greater than or equal to the 95th percentile of the distribution of the maximum temperatures across the warm season. And this definition is specific to each zip code, which means that the data controls for geographical variability. And in addition, it's also standardized based on race, age, population size, and any other characteristics that could influence hospitalization rates. So looking at the map, the dark red zip codes have the highest burden of heat attributable hospitalizations. And in general, you can see that there are higher hospitalization levels near the coast, and there are hot spots throughout the county, including more urban areas, for instance, Chula Vista or El Cajon, but also there are hot spots in some parts of northern San Diego County. So then when I say that I needed to understand the relationship between green space proxies and the heat-related health burden, what that means is performing what are called meta-regressions, and those kind of look like this graph. So we have the potential effect modifier, which is tree canopy cover here on the x-axis, and we're comparing it to the outcome of heat attributable hospitalizations on the y-axis. So this is the same exact data sets that we just looked at maps of. And here each circle represents one zip code. And you can see that the zip codes with a lower value of tree canopy cover, there tends to be higher levels of heat attributable hospitalizations and vice versa. The most important thing that we gain from doing these meta-regressions is the value of the slope. And the slope essentially tells us the strength of the relationship between these 2 variables. So it tells us if we were to increase the effect modifier, here it's tree canopy, by 1 unit, let's say we moved it from 2 to 3%, how much of the outcome variable of hospitalizations would change in response? So if we moved from 2 to 3, then the average daily hospitalizations attributable to heat would move along the slope, and they would decrease by the same value of the slope, which is 0.03. So for aim 3, which to remind you was to create future scenarios for increasing green space and then modeling their impacts on health, I first had to come up with these scenarios, which looked at a variety of different factors and indexes. So I had a long list of these scenarios. And then I had to calculate, using this relationship derived from the meta-regression at aim 2, I could manipulate the data for current green space distributions to calculate what would happen to heat-related hospitalizations with a given change in tree canopy or in imperviousness. And then I mapped these results again. So when considering future increases in green space in San Diego County, there are a lot of factors that you can take into account. So I created 33 different scenarios that differed in terms of where greening would take place, would it be consistent throughout the county or only in some locations, and so on and so forth. So I organized these scenarios into 3 discrete groups. The first one is population-based approaches, and these approaches emphasize green space proxies increasing in the same amount in every zip code in the county. Targeted approaches increase green space only in certain zip codes. So for instance, zip codes that fall below the mean in terms of the amount of tree cover, or zip codes that have the highest levels of heat attributable hospitalizations. And finally, proportionate universalism approaches deliver increases in green space to all zip codes, but of different amounts based on need. So this approach aims to make equity the main focus. As we discussed, the health burden associated with heat is unequal, with certain populations and certain regions being more vulnerable. So this approach aims to minimize those inequalities by delivering the largest increases in green space to the zip codes of, say, lower socioeconomic status, and deliver smaller increases in green space to zip codes of higher socioeconomic status. So this figure summarizes the results of all 33 scenarios. And for each scenario, I calculated first how many hospitalizations are avoided across the county as a result of that intervention. And that's depicted in the left with the blue bars. And then next, I calculated what the relative change in hospitalizations would be when this value is compared to the baseline pre-intervention hospitalization data. And the spread of those results are depicted in green here. So on average, I found that the total benefits in terms of avoided hospitalizations across all of the scenarios was 176.4 avoided hospitalizations per 100 heatwave days. And the benefits on average tended to be higher in the population-based and proportionate universalism approaches when compared to the targeted approaches. The takeaway here is that there's not really a one-size-fits-all approach to greening strategies. Rather, there are countless ways that they can be implemented. And nearly all of the strategies that I calculated had beneficial effects in terms of reducing hospitalizations. Although certain scenarios seem to have better results, and I would recommend perhaps that San Diego choose population-based or proportionate approaches, the choice really depends on the needs of any given city. Finally, I just wanted to share a couple of the maps I made representing each of the different scenarios so you can visualize what these greening strategies might look like. So these two are an example of population-based approaches wherein green space was increased by 15% in all zip codes. So on the left is a scenario where tree canopy was increased by 15%, and on the right is a scenario where imperviousness was decreased by 15%. So you can see that the areas of dark green have the highest levels of avoided hospitalizations per 100 heatwave days. And these maps are actually pretty similar to the next two examples here, which are of proportionate universalism-based approaches, wherein green space intervention was allocated based on need. And in these two examples, green space was increased according to the level of housing burden in each zip code. And housing burden is essentially just the percent of the population in that zip code that's heavily burdened by housing costs. So it's a way of measuring socioeconomic disparity. So for this strategy, those with the highest housing burden received a 30% increase in tree canopy or a 30% decrease in imperviousness. And those with the lowest housing burden received only a 10% increase or decrease. And then zip codes in the middle received an intermediate amount of change. So to conclude, I just want to highlight the importance of the study, which is the first effort to quantify the total benefits associated with multiple greening strategies at such a fine scale in relation to heat-related health impacts specifically. And these results show that green space can have a significant impact on decreasing the number of avoidable hospitalizations that occur during heat waves. Depending on different type of scenario, the results differ quite a bit, but it's obvious that there's many different options for decision makers who are looking to implement greening strategies. And as the world warms, heat waves are becoming more frequent, intense, and are going to last longer. So cities really need to act now to implement effective and actionable heat adaptation strategies, and this proves to be one way that they actually can. Also, I want to highlight that the benefits of increasing green space may actually be even larger than the study makes it seem, as hospitalization data is only the tip of the iceberg. There are likely many individuals who experience the ill effects of heat and don't seek medical treatment. And those people would not have been included in my data, but these interventions would of course help them too. I also did not look at mortality, but just as we show that there's a decreased level of morbidity with these interventions, there would likely also be decreases in mortality. I'm also only quantifying the health benefits related to heat, but countless studies have looked into the many other health benefits associated with green space, from improved air quality to improved mental health. So those benefits would be seen as well. Lastly, I just wanted to note that although these results are extremely promising, it's worth noting that implementing improvements in green space can and does sometimes come with unintended consequences. Constructing something like a new park in an underserved neighborhood can lead to increased property values, which leads to gentrification, pushing out the very people who may need the benefits of green space the most. So cities need to be extremely careful on how they implement greening strategies, and it's imperative that they work directly with the communities involved. And in some cases, particular strategies such as lining streets with trees might be better than building a brand new park. And green space is only one method for reducing the impact of microurban heat island effects, and there are many others that can and should be used in conjunction with green space implementation for best results. So I just want to thank my committee, Tariq, Mark, and David, and everyone involved in the MAS CSP program. It's been a really amazing experience being in this program, and thanks so much for attending my talk, and I'm happy to answer any questions.
Great job, Maren. That was amazing. We have some questions coming in. We have just about 3 minutes for Q&A. So I'll start. Morgan asked, are the types of green space considered? Like, what types of trees or vegetation, if they're native or not to the region, doesn't matter? Are you able to shed some light into that?
Yeah, sure. So this study didn't actually look at whether the trees are native or not to the region. That's actually a really interesting point. I used a couple different proxies. Some of them just measure greenness in general, so that would count any vegetation. And also tree cover would count any trees, not necessarily native ones. But I think you bring up a good point. If we're going to implement greening strategies, we should probably incorporate native biodiversity, especially being in Southern California where water resources are limited. We should consider implementing strategies that use plants that don't require much water, that are also native to the San Diego region. It's a good point.
Great, thank you. And right along those lines, Matt Costa asks, do you have any thoughts about the relative health or heat benefits of trees versus shrubs?
That's an interesting point, because obviously shrubs wouldn't provide the same benefits in terms of shade as, a full-grown tree. So yeah, I didn't necessarily account for like the height of the canopy in terms of trees versus shrubs in my analysis, but yeah, that could definitely have an effect in terms of health benefits, and that might be a good place for this research to go in the future.
Awesome. All right, and last question that we have time for is from Zev Brook, who asks, with summer coming up and everyone stuck indoors due to COVID-19, how is this going to impact heat adaptation strategies?
Yeah, that's actually a really interesting question, and it's something that I talked about in my report a little bit. So basically, with COVID-19, everybody is having to stay inside due to, shelter-in-place orders, and this is going to be an issue in the summer, as every year we seem to break records in terms of temperature, and it's no surprise that this summer is expected to be the hottest on record again. So with everyone inside, it's not looking good in terms of heat and health outcomes. Some cities, like New York City, have actually taken some steps already to address this. I think they're providing free air conditioning units to a lot of low income and elderly households who might not be able to leave their homes. And they're also being sure to implement social distancing guidelines at like cooling centers and things like that. So it's definitely challenging cities in terms of how they adapt to heat. And I think what COVID-19 really highlights is that cities really need to implement heat adaptation strategies now, as soon as they can, in order to, build more resilient cities and account for these unexpected circumstances that might even worsen the situation, like we're probably going to see this summer.
Great. Thank you very much for your expertise and the work and time that you put into this. We really appreciated your talk, Maren.